Yes, welcome once again to the lecture. Okay, so let us move on towards our next topic, which is takeoff mass and payload. Okay, so let me erase this first because this is of no use to you. You will unnecessarily get confused over here. So, we had already derived the required rocket equation in the previous class. Now, we will talk about total takeoff mass and payload. So, suppose your rocket is there, one rocket is there, and the rocket takes off from the ground. The rocket starts its journey from the ground. Then capital M naught. Capital M naught is the initial mass of this particular rocket. What does it comprise of? It comprises of a mass of payload. Okay, so this is your mass of payload. This is your mass of payload. And this is what? This is mass of rocket machinery. Okay, plus fuel. Rocket machine plus fuel mass. Okay, so small m is the mass of payload and small m naught is the mass of rocket machine along with fuel. Okay, so that's what is the meaning of initial mass with fuel but without payload, and this is payload. So this is your total initial mass. Okay, so it is capital M naught, small m naught plus m, that is total initial mass. Small m is mass of payload, small m naught is initial mass with fuel but without payload. Now F m naught plus m is equal to capital M, that is total final mass. Now what does it mean? So when the rocket takes off from the ground, suppose rocket is there on the ground and after that it takes off from the ground. It takes off from the ground and it reaches a certain height. Then what will happen? After reaching this certain height, surely there will be a reduction in mass because fuel will be burnt. Okay, so obviously the reduction in mass will be over here. Reduction in mass of rocket will be in this particular area, that is rocket machine plus fuel mass. So as fuel will be burnt, so this mass will be reduced. Okay, this particular mass will be reduced because fuel will be burnt while rocket is traveling. So your m naught will decrease, but this particular thing, that is your payload, it will remain unchanged because people sitting inside the rocket, which is called as the payload, it will not change because mass of people will remain constant even when they are sitting in the that is weight of the people will remain the same even when they are sitting inside the rocket. Okay, so this is the thing. So mass of people will remain same even when they are sitting inside the rocket. So payload mass will not change. So I will write F over here. What does it mean by F? F is a fraction. F is a fraction is smaller than 1. Okay, so rocket machine plus fuel mass, this will undergo reduction. So let us write this m naught as F m naught. Okay, as soon as I write F m naught, that means some fraction will be lost as fuel mass will reduce with time because fuel will be expelled from the tail of the rocket. So the initial m naught will turn out to become F m naught, where F is a fraction smaller than 1 but greater than 0 obviously. Okay, so fraction between 0 and 1 like 1 by 2, 1 by 3. Okay, so after burning of the fuel, suppose 1 by 3 of the mass remains, so 1 by 3 m naught will be the final mass of the rocket machine plus fuel. Some of the fuel was burnt, that's why. Okay, so F m naught plus m, that is capital M, that is total final mass. So residual mass and payload mass remains as it is. So this is after takeoff. Okay, this is what this particular situation is before takeoff. This particular situation, what is it? This is before takeoff. Before takeoff of the rocket. Okay, and this particular condition after takeoff of the rocket. After takeoff. Okay. Let us see over here. Let the residual mass of the rocket without payload or fuel is a fraction f of the initial mass including fuel. So the final mass of the rocket and the fuel without payload, that is f m naught, and the initial mass is m naught. So let the residual mass of the rocket without payload or fuel, okay, not or fuel, with fuel should come over here. Okay, make one correction over here. Okay, without payload, with fuel. Okay, let the residual mass of the rocket without payload with fuel is a fraction f of the initial mass including fuel. Okay, but without payload. It is required to accelerate a payload m. It is required, this particular rocket is required to accelerate this payload m. This payload m may be the mass of the members of the crew sitting inside the rocket. Okay, or they might be some fruits and vegetables, or they might be some missiles, there might be some atom bombs. Okay, so all these things are payload, so that will be small m. It is required to accelerate a payload m to velocity v. So this payload m will reach a certain velocity. This payload m kept inside this rocket will have to attain a velocity v. That is, the members sitting inside the rocket will have to attain a velocity v. Okay. Total initial mass with fuel without payload plus mass of payload. So total initial mass is capital M naught. Initial mass with fuel but without payload. So mass of the rocket machinery, what is this? Rocket machinery, okay, machinery of the rocket plus fuel, and this is what? This is your payload. Okay. Now after certain time, what will happen? This particular thing, as the fuel is burning, this m naught will reduce, and suppose it reduces to some fraction of the initial mass. So final mass will be, let us assume that this m naught turns out to be finally fraction of m naught, where your f is greater than 0 but smaller than 1. Okay, it is a fraction. So f m naught plus m. So mass of payload will remain as it is, because people will not lose mass as the rocket propels in the forward direction. So people will not lose mass. So mass of payload will remain as it is. But this rocket mass plus fuel, this will reduce to a fraction because fuel is burning. Okay, so it will be f m naught. Now this was capital M naught. So let us assume the final mass to be capital M. Okay. So total final mass is equal to residual mass without fuel plus mass of payload. Okay. Now we are considering the residual mass without fuel. So let us consider that the complete fuel is burnt. So this complete fuel got burnt. Then what will happen? Suppose one third of m naught was fuel, and suppose rocket machinery was 2/3 of m naught. Okay, so what will be this final fm naught? Fm naught will be your, because only rocket machinery will remain, this has already been exhausted, so 1/3 m naught has been gone, so only 2/3 m naught has remained, so it will come out to be 2/3 m naught. Okay, so your fraction f in this case is 2/3. Okay, like that. So total final mass is equal to residual mass without fuel. We are considering a situation when the entire fuel is burnt, the fuel is exhausted. In that particular case, what will happen? So total final mass is equal to f m naught plus m, where f is smaller than 1 clearly, because this 2/3 was also smaller than 1. Okay, so capital M is equal to f m naught minus m. Now this is a small m naught, this is small m naught, and this is small m naught. This is small m naught can be written as, what can it be written? It can be written as small m naught is equal to capital M naught minus small m. It can be written like this. So capital M naught, small m naught, it is capital M naught minus m. Okay, so capital M naught minus m. So this is the thing. So now this is, suppose your equation E. This is what? Suppose your equation E. Now using the equation of motion of rocket and neglecting gravitational force we have. Now what do you have in the equation of motion of rocket? Let us see once again. You have something like this in the equation of motion of rocket. Okay, you have something like this in the equation of motion of rocket. Now suppose you neglect the gravity, then what will happen? If you neglect the gravity, then this term will vanish. This term will vanish. So only thing which will remain after you neglect the gravity is this. So let us see. Now using the equation of motion of the rocket and neglecting gravitational force, we have V equal to U relative ln m naught over m. Then V equal to U relative. Now in other exams, in some other exam, what will you do? You will actually write minus gt over here. Okay, in some other exam you will write minus gt over here along with this. Then you will say that gravitational force is 0, so g equal to 0, and then you will arrive at this step. But in the IAS physics optional, actually as soon as you write that the neglecting gravitational force, we are writing, so as soon as you wrote that neglecting gravitational force, it is understood that minus gt term will not come over here. So this is quite obvious step, so no need to further elaborate that there is minus gt then g equal to 0, because this is the situation. No need to elaborate in such a long manner. Okay, this is the succinct way of writing the answer. So V equal to U relative ln m naught over m. Now V equal to U relative ln. Now capital M naught. What was your capital M naught? Small m naught plus m. Okay, and your capital M was, as already found in the previous slides. You have already found, right? What you have found out? You have found out capital M to be equal to this much. And what about m naught? M naught is this much. Okay, m naught plus small m. So you substitute these values over here. Capital M naught equal to m naught plus small m, and capital M is equal to f times m naught minus m plus m. This is the thing. So what will happen then? You will take this U relative to the left hand side. It will become V by U relative. Then ln this much. Then over here ln means log to the base e. So over here there is base e. So e to the power V by U relative is equal to this much. Okay. So I don't think there is any need. Then you will take the reciprocal. So you will finally get something of this kind. Then m0 will go over here, this m0. Okay, so this is further manipulation of the same thing. So f multiplied by this, so this and this term you will take together. Okay, you will open this bracket and f m0 you will keep over here, and minus fm plus m, you will take m common. So m times of 1 minus f equal to m0 e to the power minus v by u relative. So what did you get? You got capital M0. You got capital M0 to be equal to m times of 1 minus f divided by, okay, got it? So you can see actually this particular term, how will you get it? Take both these things to the LHS, okay? This m0 term and this m0 term, take them on one side of the equation and this term on the other side of the equation. You will get this. After you take capital M0 common from these two terms, you will get this. So these are just mathematical manipulations. No need to elaborate all these things. I think these are just elementary facts. Now, so what is this expression? This is the expression for initial mass of the rocket. What was your capital M0? Let us see over here. Okay. Total initial mass of the rocket. Okay. Total initial mass of the rocket. So the expression for total initial mass of the rocket you have obtained over here. This is the expression for total initial mass of the rocket before takeoff. Total initial mass of the rocket before takeoff. And you have found it in terms of payload. Okay, initial mass of the rocket before takeoff, you have found it to be in terms of this payload mass. Okay, because small m is the mass of payload, right? Small m is the mass of payload, you can see over here. Small m is the mass of payload and capital M0 is the total initial mass of the rocket before takeoff. So you have found out this capital M0 in terms of small m, that is total initial mass of the rocket before takeoff in terms of mass of payload. So you found this. What is a multi-stage rocket? What is the limitation of a single? Let us see this question. What is a multi-stage rocket? What is the limitation of a single stage rocket? Or the question can also be asked like this, that show that final velocity of a multi-stage rocket is much greater than that of a single stage rocket, okay, of the same total weight and fuel supply. So what does it mean is that there is a single stage rocket. Now what is a multi-stage rocket? Single stage rocket, you all know that all the rocket, the complete rocket is a single piece rocket. There are no pieces attached to the rocket, okay. So such a rocket is single stage rocket, means only a single body throughout the rocket, single one piece body, okay, that is called single stage rocket. What is a multi-stage rocket? That is suppose you have 3 or 4 parts of the rocket, okay. So one part is discarded, then second part is discarded, then third part is discarded, then fourth part remains, like that, okay. So multi-stage rocket is not one piece rocket. Multi-stage rocket is not one piece rocket. It is made up of comprising parts, okay. Multi-stage rocket is made up of comprising parts. Now if the weight of the rocket initially for a single stage rocket and for a multi-stage rocket, if the same total weight is there initially and the fuel supply is also the same, then you will have to show that the multi-stage rocket attains a much higher velocity as compared to a single stage rocket. This is the thing which you have to show over here, okay. Now a multi-stage rocket is just a combination of rockets either joined successively in series. Now what is the meaning of this? So let me take a new slide. Let us see what is a multi-stage rocket. So multi-stage rocket is just a combination of rockets either joined successively in series. So let us draw the diagram. Okay, joined successively in series. So suppose you have a rocket like this. This is what? Joined in series. These are joined in series. Then one inside the other. What kind of rocket is this? Suppose you have this kind of rocket. Then there is one more part inside the rocket. Okay, so as the rocket drops this, the velocity of rocket increases after that. Okay, so this is one inside the other. This is inside this is inside this. Okay, this is inside this. Okay, with rear part of one inside the nozzle of the other. Now what kind of rocket is this? With rear part of one. Okay, with rear part of one, with rear part of one inside the nozzle. Okay, so rear part of this rocket, this particular part, this rear part is inside the nozzle of this particular part. Okay, it is inside the nozzle of this particular part. This particular part, okay, is inside the nozzle of this. So these three kind of rockets might be there. That is those successively joined in series, one inside the other, with rear part of one inside the nozzle of the other. So such is the case of multi-stage rocket. In order to attain higher velocities, the rocket is designed in stages. When the fuel of the first stage is exhausted, so in order to attain higher velocities, rocket is designed in stages, means in pieces. Okay, in pieces. When the fuel of the first stage is exhausted, its rocketing casing is detached and drops off. So suppose this is your first stage. Suppose this particular thing, let me mark it with yellow color. So this yellow color is suppose your first stage. Then what will happen? When the fuel of the first stage is exhausted, its rocketing casing is detached and drops off. So when fuel of this particular yellow colored thing is exhausted, it is detached from here and this part is dropped off. Okay, then fuel of this part will be exhausted after some time. Then this part will also be dropped off. Then fuel of this part will start to be exhausted. Okay, then this will also be exhausted once. It will be also be dropped off then, and finally this will remain. Okay, so it is a 4-stage rocket. Clearly, when the fuel of the first stage is exhausted, its rocketing casing is detached and drops off. Okay, now let me see just a second. Okay, the velocity so far attained becomes the initial velocity of the second stage. So the velocity, so this is this kind of rocket you have, right? This is a 5-stage rocket. So when this part of the fuel over here is, when it is exhausted, this part is detached. Then when fuel of this part will be exhausted, this part will also be detached. But the final velocity which was attained while this part was being the fuel of this part was being exhausted. Okay, the final velocity which was attained when the fuel of this part was being exhausted, so that will be the initial velocity of this particular rocket. Okay, So suppose let me write properly. Okay, suppose you have a rocket of this kind. Okay, and suppose fuel of this part is completely exhausted. So it at t equal to 0, this particular rocket was having some velocity. Then at t equal to t, it was having velocity v. So at that particular time t equal to t, this part was detached. As soon as that part was detached, so for this four stage rocket, this was the final velocity, but it becomes the initial velocity of this three stage rocket, right? V becomes the initial velocity of this three stage rocket, the three stages which remain now. Okay, so that is the thing. And drops off the velocity. Let me write over here the velocity so far attained becomes the initial velocity So if the rocket converts from 4 stage to 3 stage, then what will happen? The final velocity of the fourth stage rocket will be equal to the initial velocity of the 3 stage rocket, right? So velocity so far attained becomes the initial velocity of the initial velocity of the second stage, which is now ignited. The velocity so far attained becomes the initial velocity of the second stage, which is now ignited. So after the fuel of this part, after it was consumed, so this part was ignited. So the final velocity of this whole thing is equal to the initial velocity of this particular thing, okay, which is now ignited. The removal of surplus mass, the removal of surplus mass contained in the first stage. The removal of the surplus mass contained in the first stage considerably helps in attaining the removal of this surplus mass, okay. So suppose we have three stage rocket, suppose. So removal of this surplus mass after some time t, and this part is ignited after that. So removal of this surplus mass in the first stage considerably helps in attaining still higher velocities, because the total momentum needs to be conserved. Okay, the total momentum needs to be conserved. As the total momentum needs to be conserved, so if you momentum is equal to mv, right? Momentum is equal to mv and momentum needs to be conserved. Now your momentum p equal to mv. Now if you reduce the mass from here, then what will happen? This will reduce, so eventually v will increase. So that is the concept. The velocity so far attained becomes the initial velocity of the second stage, which is now ignited. The removal of surplus mass contained in the first stage considerably helps in attaining still higher velocities. This process continues depending on number of stages. So this particular process continues depending on the number of stages. If it is a 3-stage rocket, then two parts will be lost. If it is a 4-stage rocket, then 3 parts will be lost. Okay, from time to time, and the velocity will keep on increasing because the product mv has to be constant. So if m is reduced, v will increase. Okay. Limitation of 1-stage rocket. Now let us write limitation of 1-stage rocket. Velocity attained by a rocket when gravity is neglected. How is it given? Velocity attained by a rocket when gravity is neglected. Is given by so when equation of rocket you will write. Okay, so we are talking about actually limitation of 1-stage rocket. Velocity attained by a rocket when gravity is neglected is given by v equal to v equal to u relative ln m naught, derived already in the previous lecture. Now you know this very well. How did this come? Let me write the explanation of this over here. How this we have arrived at this particular expression. So your v is equal to u relative ln m naught over m, right? ln m naught over m, ln m naught over m minus gt. This is your expression for final velocity. Now if g equal to 0, that is the gravitational field is 0, gravity is neglected, so g will be equal to 0, then you will get something of this kind. Okay, so it is clear that the ultimate velocity of the rocket can be increased by increasing exhaust velocity u relative. So you can see over here that the ultimate velocity, which is the final velocity attained by the rocket, it can be increased by increasing the exhaust velocity u relative, or by increasing the ratio m naught over m. You can either increase the ratio m naught over m, or you can either increase the u relative in order to attain higher final velocities. So if you want to achieve higher final velocities, you can increase u relative, or you can increase m naught over m, or you can increase both u relative and both m naught over m. Okay, both u relative and m naught over m also you can increase. So your final v will increase many folds. So let us write over here. It is clear. It is clear that the ultimate velocity of the rocket can be increased ultimate velocity of the rocket can be increased by increasing the exhaust velocity u relative and the ratio from the formula you can see this clearly. That is okay. So ratio m naught over m, what is it equal to? So this m naught over this m, what is it equal to? You have already seen over here. Let us go back. So your capital M naught is total initial mass, right? Total initial mass. And what is your small m? M naught is total initial mass, and this is residual mass, right? Total final mass, that is total residual mass. So it is the total initial mass of the rocket divided by what? Divided by total residual mass of the rocket. So by increasing this ratio, that is the initial mass, that is you take very heavy rocket initially, and finally you take a very, what we can say, less mass. Okay, so you have a huge amount of fuel inside your rocket. Okay, the fuel tank is very heavy. Only then you will have such a situation, right? Because only the fuel is getting exhausted, right? So if you take very huge amount of fuel inside your rocket, only then this situation will arise, that the initial mass is very high and the final mass is very less, because fuel will be burnt out. So only if the fuel is completely burnt out, only then this situation will arise, and the fuel is very heavy. In that case, in that particular case, this situation will arise that initial mass is much higher than the residual mass after burning out of the fuel. Okay, so m naught over m ratio can be increased by taking a heavy fuel, right? So m naught over m will increase because of that. However, however, the exhaust velocity, u relative is what? U relative is your exhaust velocity. Okay, so the exhaust velocity cannot be more than 2.5 kilometer per second with the conventional chemical fields. Okay, so the exhaust velocity of the gases with respect to the rocket, that is u relative. With the current technology, we cannot have exhaust velocity u relative to be greater than 2.5 kilometer per second. Now remember this thing, please take a note of it, that we are not measuring the velocity in kilometer per hour, neither we are measuring it in meter per second. Okay, neither in kilometer per hour nor in meter per second, we are measuring it in kilometer per second. Okay, so this is a very huge unit, very big unit, that is the exhaust gases are going 2.5 kilometer in 1 second itself. In 1 second itself they are going 2.5 kilometer. So it is a very high velocity. Your car or motorcycle goes in 1 minute it goes 1 kilometer. Okay, your motorcycle, what is the speed of your motorcycle? 1 kilometer per minute. Okay, this is approximately the speed of your motorcycle, that is in 1 minute it will go 1 kilometer, but over here in 1 second itself it is going 2.5 kilometer. So it is a very huge speed. Okay, very huge, because we are talking about rocket, not an automobile. Okay, we are talking about rocket, not an automobile. That's why this is the case. There is an upper limit on m naught over m also. There is an upper limit on m naught over m also. So how there will be an upper limit on m naught over m? Okay, suppose you want to say that I want to keep the fuel to be very heavy. Suppose there is fuel filled inside this. Okay, after burning of the fuel, this is the mass after burning of fuel, and before burning of fuel, along with fuel, this is the mass. So this is total initial mass and this is total residual mass. Now if I make the rocket in order to keep the initial mass very high, I will have to keep a heavy fuel. Okay, and if total residual mass, the limitation is that in order to keep a heavy fuel, you have to make a heavy rocket so that the fuel is held by the rocket. Okay, so as soon as you make a heavy rocket in order to keep a heavy fuel, in order to keep a heavy fuel over here, if you keep the rocket to be very heavy, because light rocket cannot bear the heavy fuel. Light rockets cannot bear the heavy fuel, right? So if you want to increase the mass of fuel so that your residual mass is very low, you will have to keep heavy fuel, and in order to keep heavy fuel, you cannot keep very light rocket in order to keep a heavy fuel. So the rocket should also have a considerable mass. As soon as you say that the rocket has a considerable mass, the thing is total residual mass will increase, so this ratio will decrease. So there is a limit on this m naught over m ratio. Okay, there is an upper limit on m naught over m also. As the rocket shell must be strong enough as the rocket shell must be strong enough to hold the fuel. So the rocket shell must be strong enough in order to hold the fuel, because the fuel should be heavy. If you want a heavy fuel to be kept in a rocket, then the rocket should also be heavy. If the rocket is heavy, then the residual mass, that is the final mass after burning out of the fuel, that is also heavy. Okay, so there is a upper limit on m naught over m. You cannot say that I will keep this very low, I will make this zero itself. Okay, you cannot say like that I will make this particular term to be zero itself. You cannot do like that. Okay, so as the rocket shell must be strong enough to hold the fuel, in actual practice the ratio m naught over m, the ratio m naught over m cannot be greater than 4. With the current advancements. Okay, with the current technological advancements. Therefore, maximum velocity of the rocket at burnout. At burnout is V equal to 2.5 ln4. Okay, how has this arrived? How we have arrived at this result? You can see over here. In the place of u relative, what will you put? You will put 2.5, and in place of m naught over m, you will put 4. Okay. Why you will put like that? Because those are the maximum attainable values. As soon as you put maximum attainable values, of u relative and m naught over m, what will happen? You will get the maximum attainable value of v. Okay. So let us see. V equal to 2.5 ln4, because u relative can be maximum 2.5, m naught over m can be maximum 4. So maximum attainable velocity of the rocket at burnout is like this. Okay. So 3.5 km per second is the maximum velocity of the rocket at burnout. So rocket cannot have velocity higher than 3.5 km per second. I am talking about a conventional rocket. I am not talking about NASA rocket. Okay, NASA rockets are very fast. They are very, very fast. They go 35,000 km per second, like that. Okay, not per second, but 35,000 km per hour, like that. Those are the speeds of NASA rockets. But we are talking about a conventional rocket. Okay, conventional rocket, which is used in everyday life, not in space explorations. This rocket which we are talking about, this is not used in space exploration. Okay, so this is a conventional rocket. So this is quite obvious. So V is clearly less than escape velocity of the Earth. What is the escape velocity of Earth? Escape velocity of Earth is 11 something around approximately 11 km per second. That is the escape velocity of the Earth, right? So V is clearly less than escape velocity of the Earth. Okay. So you had to tell the limitation of one stage rocket. Okay. So this is what these expressions which you have found out. These expressions are for one stage rocket. Okay. Now one stage rocket could not achieve. One stage rocket, through calculations we have found that one stage rocket cannot attain velocities higher than 3.5 km per second. So it cannot escape the Earth's atmosphere. What does it mean by escape velocity? Escape velocity is the minimum velocity with which an object must be thrown so that it escapes the Earth atmosphere, Earth's gravitational field. So if you throw a ball with the speed of 11 km per second from the surface of the Earth upwards, okay, suppose this is your Earth, and if you are standing on the Earth, and if you throw a ball with a speed 11 km per second, then what will happen? That ball will escape from the earth's gravitational field. It will go in the space. But if you do not do so, if you uh, throw a ball with a velocity much smaller than 11 km per second, then what will happen? The ball will return back on the surface of the earth. Okay, if you throw a ball with velocity smaller than 11 km per second, then the ball will go upwards and come down on the surface of the earth once again. But if you throw a ball with a velocity higher than 11 km per second or equal to 11 km per second, then what will happen? The ball will go in the space. It will leave the earth's gravitational field. Okay, so that is called as escape velocity. So wait a second, let us erase this. So it is, so first stage rockets cannot attain this is the limitation of first stage rocket. Okay, this is what is the limitation of first stage rocket. So first stage rockets cannot attain higher speeds. Higher speeds for the same total weight and total fuel supply. For the same total weight and total fuel supply. Okay, so the first stage rockets cannot attain speeds higher than 3.5 km per second, as already found out. So they cannot leave the earth's gravitational field. They are not able to leave the earth's gravitational fields because they are not able to attain velocities higher than 3.5 km per second, 11 km per second. They can attain maximum velocity 3.5 km per second. Okay, so first stage rocket cannot attain higher speeds from the same total weight and total fuel supply. Okay, so we will learn in some time. Okay.